Good morning. Welcome to the third session of Diverse Node Mobility Front-End Development Program. So in this session, we will cover the continuation of Module 3 that talks about flow control, more data types, and the computer logic. And also the introduction for Module 4, which talks about aggregating data into arrays. But before we start, did you study the last part of module 2 and 3? Because this is, if you are going to, study about this session or listen to this session, you need to listen first to the previous session because it is a prerequisite. So here, I'm going to share my screen to you. Right. Right. Here, we are going to continue the last slide. Hold on. So, in the last session, we talked about the more data types that include short, long, and the other floats, and double, and character, or which stands for char. And we also studied about the logic, computer logic that includes AND, OR, and XOR, and the updated table that includes unary and binary. Right. So we are already done with this one. So we also tackle about the loop, the do while loop, the if else, and for loop, right? I think we're getting closer to the last slide that we have discussed before. And by the way, guys, if you have any questions, or if you want to discuss something like uh, that is that talks about the idea, the logic operation, or maybe the logic operation, or maybe the operators you don't understand, you can post it via courses, and then the left left menu you can choose discussion, and you can post it via discussion, and I will answer that for you. And we also discuss break and continue code that is also a reserved keywords, continue, and break. I think we're getting closer. Do you still remember here the bitwise operations? Just wait. Right, so let's continue, guys. I think this is the last slide that we have tackled last time. Right, so here we are going to continue the computer logic. Let's have a look at this at an example of the difference in operation between logical and bit operations. Let's assume that the following declaration has been performed. So in this snippet, as you can see, it is there are two variables that have value, and that is I and j, and there are integers. So it was written in the declaration, int I is equals to 15 and j, and comma j is equals to 2 and then semicolon. So if you assume that the ints are stored with 32 bits, then the bitwise image of the two variables will be as follows. So here, as you can see, it is zeros and ones. So if you are going to convert it, because this number is decimal, and if we are going to convert it into binary, which is ones and zeros, so probably this would be the answer. This would be the equivalent of that. So binary numbers can only be read by computers, and it has the meaning, it has their own meaning for them. For example, 15, the number of 15 would be this numbers of 0 and 4 and 1 1 1 1 1. And for 22, it is equivalent like this, 1 0 1 1 0. So we have the declaration, and it is given as int log is equals to I and end and j. So do you still remember what is the meaning of j? That is read as and, right? And as we preview the table here, if you are going to use end, so probably the answer for left and right, if it's 0, then 0. Then if it's 0 and 1, so probably the answer would be 0. 1 and 0 and 0. So, and 1 and 1 is 0. So all you need to remember is the only answer for 1 is if it is the same, which is 1 and 1. So here we're dealing with the logical conjunctions. Let's trace the course of calculations. Both variables I and j are not zero, so will be deemed to represent truth. If you look at the truth table for the AND operator, we can see that the result will be true, and that's it's an integer equals to 1. This means that the bitwise image of the log variable is as follows. So let's have the next slide. Now the bitwise operation, here it is. So int bit is equals to I and j, and the operator and the ampersand operator will operate with each pair of corresponding bits separately, producing the values of the relevant bits of the result. Therefore, the result will be as follows. So here, because as you remember the AXI code, so it is just like that, but it has its own equivalent when it comes to binary. So this bits corresponds to an integer value of 6. Let's try the negation operators now. First the logical one. Int log neg equals not I. So this is a negation, which means not. Then the log neg variable will be set to 0, so its image will consist of zeros only. Int bit neg equals negative I. And then it may be somewhat surprising that the bitneg variable value is -16. Strange? Not at all. If you're surprised, we hope it will be an incentive for you to immerse yourself in the secrets of binary numeral system and rules governing choose complement numbers. So 00 here, this is the log neg, this is the bit neg. So let's each, uh, here's the example of two complement numbers. Here, each of the previous two argument operators can be used in their abbreviated forms. The following notations are equivalent, respectively. X is equals to X and Y. X is X or Y. X equals X XOR Y. X and equals Y. X or equals I. X XOR equals Y. We'll now show you what bitwise operators are good for. Imagine that you're a developer who has to write an important piece of an operating system. You've been told that you have to use a variable declared in the following way: int flag register. So here in the snippet, as you can see, this is an integer and the variable name is var flag register. The variable stores information about the various aspects of system operation. Each bit of the variable stores one yes or no value. You've also been told that only one of these bits is yours. Bit number 3, 3. Remember that the bits are numbered from 0 and bit number 0 is the lowest, while the highest is 31. So we have 32 bit numbers, but it doesn't mean that it is 1 to 31. It means like a 0 to 31. So the remaining bits are not allowed to change because they're meant to store other data. See, here's your bit marked with the letter X. Here, let's go to another slide. All right, so you may face the following task here. Check the state of your bit. You'll want to find out that the value of your bit comparing the whole value variable to 0 will not do anything, because the remaining bits can have completely unpredictable values, but we can use the following conjunction property. So x and 1 is equals to x and 0 is equals to 0. If you apply the AND operation to the flag register variable along with the following bit image, so it will prompt us as a snippet. Note that the one at your bit's position, we obtain one of the following bit strings as a result. So here, as we said, that this would be the result of the binary number. So if your bit was set to 1, so if your bit was set to 1, so it will result as this one. And if your bit was set to 0, then um, uh, this if your bit was set to 1, then it probably produces result, and if it is 0, then this a sequence of 0 a sequence of zeros and 1 whose task is to grab the value or to change the selected bits is called a bit mask. Let's try to build a bit mask to detect the state of your bit. It should point to the third bit. That bit has a weight of 2 to the power of 3 is equivalent to 8. A suitable mask could be created by the following declaration. Int the mask is equals to 8. So here we have the variable named the mask, and it has a declaration value which is 8. And we can also make a sequence of instruction depending on the state of your bit. Here it is. So here's the snippet of pseudocode, just like if, and then open and close parenthesis, flag register, and the mask. and write your code here, which my bit is set, and then else, and bit, my bit is reset. So that is an example of how we the sequence of the instruction, and it will depend on how the logic will be, your program will be. Right, so how about reset your bit? So you assign a 0 to the bit while all the other bits must remain unchanged. We will use the same property of the conjunction as before, but we will use a slightly different mask exactly as below. So here, as you can see, we have mask the this value. So it was masked 0. So the mask was created as a result of the negation of all bits of the mask variable. Setting the bit is simple and looks like this. Choose the one you like more. So here, flag register is equals to flag register and negation, the mask. Flag register and equals negation, the mask. So it has the same logic, as you can see. You can choose whatever statement you want, but it will prompt you the same result. So here, let's set your bit. You assign a 0 to your bit while all the remaining bits must remain unchanged. We will use the following disjunction property. So here, x or 1 is equals to 1, and then x or 0 is equals to x. So that is the example on how to set your bit. We're ready to set your bit with one of the following instruction. A flag register equals flag register or the mask, or flag register or equals the mask. So let's negate your bit, or let's have the opposite of your bit. So you replace a 1 with a 0 and a 0 with a 1. We will use an interesting property of the XOR operator. So x XOR 1 is equals to not x, and then x XOR 1 is equals to x. And negate your bit with the following instructions. So here's the instruction. We can negate it by using this statement. Flag register is equals to flag register XOR the mask, or flag register XOR equals the mask. So this two statements have the same logic operation in the computer. So let's have the next slide. So let's have bit shifting. The C language offers yet another operation relating to single bits shifting. This is applied only to integer values, and you must not use floats as arguments for it. You use this operation very often quite unconsciously. How do we multiply any number by 10? Take a look. 1, 2, 3, 4, 5 times 10 is equals to 1, 2, 3, 4, 5, 0. As you can see, multiplying by 10 is in fact a shift of all digits to the left and filling the result gap with a 0. Division by 10. Let us look. 1, 2, 3, 4, 0 divided by 10 is equals to 1, 2, 3, 4. Dividing by 10 is not more than shifting the digits to the right. The same kind of operation is performed by the computer, but with one difference, as 2 is the base of binary numbers, not 10. Shifting a value 1 bit to the left corresponds to multiplying it by 2 respectively. Shifting 1 bit to the right is like dividing by 2. Notice that the rightmost bit is lost. Bit shifting can be two things. So the first one is logical. If all bits of the variable are shifted, shifting takes place when you apply it to the unsigned integers. We can set it as arithmetic. So bit shifting can be arithmetic. If shift omits the sign bit in two complements notation, the role of the sign bit is played by the highest bit of the variable. If it's equals to 1, the value is treated as a negative. This means that the arithmetic shift cannot change the sign of the shifted value. The shift operators in the C language are a pair of diagrams, so we can have greater than and less than, a value greater than bits and value less than bits. Here clearly suggesting in which direction the shift will act. The left argument of these operators in the integer value whose bits are shifted. The right argument determine the size of the shift. This shows that this operation is certainly not commutative. The priority of this operation operators is very high. You'll see them in the data table of the priorities, which will show at the end of the session. So this operation, the left argument and the right argument is have a higher priority in the operators. Let's assume that the following declarations exist. So we have and we have the variable sign, and its value is equals to -8. And we also have integer variable name var s. So we have unassigned, and the variable name is unassigned with a capital U. And we have a value of 6 and var u, another variable for unassigned. Take a look at these shifts. They are shown in editor. So both operators can be used in the shortcut form as below. So here, as you can see in the snippet, we have sign, then right argument. So this is read as right argument equals 1 and then semicolon. So we have the comment as you read it. This is division by 2, and sign left argument equals 1. So this is multiplication by 2. And here's the updated priority table containing all the operators introduced in this section. So as the slide mentioned earlier, this is the updated priority table. So we have here, there's the left argument and the right argument. So as you can see, it is one of the higher priority in the priority table. So let's have the next slide. All right, so it is now time to test your knowledge. We will answer Module 3 quiz, and after that, please answer also the Module 3 test. All right, so guys, I'm going to post this one, and let's have our next session, our next module for Module 4. Right, please answer the Module 3 quiz and Module 3 test. All right, as we continue this session, let's have Module 4, and it talks about aggregating data into arrays. So in this module, you will learn about switch, different phases of if, arrays, which is the vectors, and sorting in real life and computer memory, initiators, pointers, an address, a reference, a dereference, and the size of operator, simple pointers, pointers to nothing or null, the AND operator, the pointer arithmetic, pointer versus array, different forms of the same phenomenon, strings and string manipulation. So let's have the first slide of this module. So we have case and switch versus if. As you already know, an if cascade is the name of the construction of code where many if instructions are placed consecutively one after another. As in the example in the editor, of course, there are no obstacle to using and maintaining code like that. But there are few disadvantages that you might not want to have to deal with. For one, the longer the cascade, the harder it is to read and understand what it's intended for. Amending the cascade is also hard. It's hard to add a new branch to it, and it's hard to remove any previously created branch. But the C language offers a way to make selection easier. We want to emphasize that this is really more syntax candy than anything else. You can manage without it, but don't hesitate to use when your if starts growing extensively. So as you can see here in the Edge of Interactive, here in the editor, we can see that it is a if statement. So we have if and we have three else here. So it has a lot of condition. So let us read this one. If if I is equals to 1, then we are going to put the statement only 1. And then else if I is equals to 2, then puts I want more. And then else if I is equals to 3, then puts not but. And else if it is not equals to 1, 2, or 3, more than or less than between those numbers, then puts okay. So that would probably the result of the condition of this code. Okay, so let's have the next slide. So let's take a look at the snippet in the editor. It's an example of how to replace an if cascade with a specialized instruction. Note that the words switch and case are keywords. Okay, remember that switch and case are reserved keywords. The new instruction is called switch, and it is in fact a switch. Yes, it is literally a switch. So how does it work? So first, the value of expression enclosed inside a parenthesis after the switch keyword is evaluated. This is sometimes called switching expression. Then the block is searched in order to find a literal preceded by the case keyword which is equal to the value of the expression. When this case is found, the instruction behind the colon is executed. If there's a break among them, the execution of switch statement is terminated. Otherwise, all instructions are executed until the end of the block is reached or another break is met. What happens if the switching expression has a value that does not occur in any of the cases? The answer is simple. Nothing will happen. None of the branches of the switch statement are executed. So here, as you can see in the editor, we have the variable I. So we can switch its condition. Switching is also a conditional statement. So if we have a case 1, let's put only 1 and then it going to break, or it means just like to pause the execution of the program. And when it comes to case 2, so as you can see, we have no number, right? No, we have no value of the case. But as you can see here on the previous if else, we have equals equals 2, 3. But in the switch, it is literally or exactly the value after the case. So if case 1, so the value would be 1 if I is equals to 1, then puts only 1, and then case 2 puts I want more, and then 3 puts not bad, then it will be post, and 4 puts okay. So as you can see in the 4 cases, we have 3 breaks, and we don't have break in the last case. So since this is the last case, you don't need to put break. or it will depend on the situation. If you like to put and it has a lot of or another loop or another condition to do. Right, so let's modify the requirements. We will assume now that our program is satisfied and it is says okay. If the I variable is equals to 4 or 3, does this mean that we have created two branches for both possibilities? Fortunately not. We're allowed to place more than one case in front of any branch, like one in the editor. All right, so as you can see, um, yeah, fortunately not, and we're allowed to place more than one case in front of the any branch. Wait, so just take note that case and switch is a reserve keywords, right? So we can also assume that our program does not have an opinion when I values are different from ones specified so far, and we want the program to express in a clear form. Have we made a million new cases covering the entire in types range? No, we can use a generalized case that covers all these events which haven't been enumerated in the previous cases. Take a look at the code in the editor. Note the default is a keyword too. Okay, so where's the default? So as you can see, it was placed under the fourth case. So here's the default. Don't forget to use the break, leaving out this keyword in one of the most common mistakes developers make, not only in the beginning of their careers. Simple, right? And how elegant. But now, a few more important remarks to note. The value after the case must not be an expression containing variables or any other entities whose values aren't known at the compilation time. The case branches are scanned in the same order in which they are specified in the program. This means that the most common selection should be placed first. In fact, this could make your program a little faster in some cases. Now we say goodbye to our switch statement. It's time to take up an important challenge we're going to discuss already. So here, you need to take note of these important remarks in switching statements. Right? So for the next one, vectors, why do you need them? Or array, why? There may come a time when we have to read, store, process, and finally print dozens, maybe hundreds, perhaps even thousands of numbers. What then? Must we declare a separate variable for each value? Will, will we have to spend long hours writing statements like the one here? In var 1, var 2, var 3, 4, 5, 6, 7, 8. What if it's 1,000 or 1,000 or millions of variables? So if you think this is a simple task, then we suggest that you take a piece of paper and write a program that reads 5 numbers of type int and prints them in order from the smallest to the largest, and this is called sorting. We don't think your piece of paper will be big enough for the task. So far, we've declared variables that can store exactly one given value at a time. These variables are called scalars, analogous to mathematical terms. All variables we've used so far have actually been scalars. Think of how convenient it would be if we could declare a variable that can store more than one value. Uh, for example, 100,000 or even 10,000 variables, it would still be one of the same variable and being very wide and extensive. Those that sound appealing, perhaps, but how would it handle all these different values? How would it choose just one we need? Just should we just number them and we'll say give me the value number 2, assign the value then number 15, increase the value number 10,000. Maybe what do you think? We will show you how to declare the value variables. We'll do this with the example that we suggested before. We will try to write a program that sorts a sequence of integers, but we won't be particularly ambitious right now. We will assume that there will be 5 numbers. We read this record as follows. We created a variable called numbers. It is intended to store 5 values, note that a number enclosed inside a bracket of type int, which we know from the keyword int at the beginning of the declaration. Let us say that the same thing using the appropriate terminology. Numbers is an array consisting of 5 values type int. Since such an array is called a vector in mathematical terms, we will also say that this statement declares an int vector of a size equals to 5. So all the elements of an array have the same type. There are no exceptions to this rule. There are other programming language which allow to use the arrays of with elements of various types, but C is not one of them. It is you might it is not, but as you might think a troublesome limitation, it can be effectively avoided if necessary. However, this is a very complex subject, and you have to wait some time for the solution to this puzzle. It's time for a bit of intrigue. The C language adopted the convention that the elements in an array are numbered starting from 0. This means that the item stored at the beginning of the array will have this number 0. Since there are 5 elements in our array, the last one will have the number 4. Don't forget this. However, you'll soon get used to it and it will become second nature. So we have 5 elements, and the first element and its index is 0. Second element, its index is 1, and the third element is index 2. The fourth element, its index is 3, and the fifth element is its index is equals to 4. So before we go any further, we have to note the following are vector is collection elements, but each element is a scalar. All right, so in having the array, we will use this symbols. It is a bracket, square bracket. So that stands for array, or the symbols for array. So how do we assign a value to those elements of the array? Let's assign the value of 111 to the first element of the array. We do it this way. So we have numbers, and then here a bracket 0 and equals to 1. So as you can see, the task is assign the value of 111 in the first element of the array. So as you still remember that the first element, the index of that is 0, right? So that answers the question why it is bracket 0. So here, so we have the assigned value. The first element of the array is 111. So we need a value stored in the third element of the array, and we want to assign it to the variable I. This is how we can do it. So I is equals to numbers, and then bracket, then 2. So in this task, we need to in the third element, and we assign it to the variable I. So as you can see, it is the third element, which is 2. The index is 2, and then we will assign it to I. So whether it is number, bracket, and equals, just like this one, it has the same. We can interchange this one, right? So we can have the value of the array will be here, and we can have in the front of the array. And the separating operator will be the equal sign, right? And don't forget about the semicolon. And now we want the value of the fifth element to be copied in second element. How can you guess how to do it? So here the task would be, we want the value of fifth element here, fifth element, to be copied in the second element. So here, so on how to do it, it is just like numbers and then bracket 4 and equals to numbers bracket 1, or yes, we can interchange that. So the value inside of the brackets, which selects one element of the vector, is called an index, while the operation of selecting an element from the array is known as indexing. Uh, all the index set or the, all the indexes we've used so far have been literals. Their use are fixed at runtime, but any expression could be in the index too. This opens up lots of possibilities. Great. So let's have the next slide. Okay, so we want to calculate the sum of all the values stored in the numbers array. So remember that this number is a variable name. We declare a variable where the sum is stored and initially we assign a value of 0 to it. Its name is a sum. So here, as the program declare that the value is for sum is a sum which is stored and initially assigned with 0. So here it is initially assigned uh, uh, assigned with a value of 0, and then we add it in the elements of the array using the for loop, which is a great tool for processing arrays. Take a look at the snippet in the editor. Let's talk a bit about this example. So the I variable will take the values 0, 1, 2, 3, 4 in that order, and hence we're indexing the numbers array. This is the number array. Selecting by the subsequent element, the first, second, third, fourth, and fifth. Each of these elements will be added by the plus equals operator to the sum variable by giving the final result at the end of the loop. Great. So here in this example, we have declared the array, which is numbers, and it uh, into the uh, with a value 5, and we have sum and it's equals to 0, and we have I variable. So we are going to use for loop, and just like we have learned in the previous session, what is the syntax for loop. So for the for loop, we are going to use the operators equals, then greater, or maybe less than, and then increment or decrement. So in this case, we have I is equals to 0, and then it is divided between semicolon, so I, and then maybe it is greater or less than 5, and then I increment. So sum is equals is, or maybe we can write it as sum equals sum plus numbers, number array numbers I. So we can if you are going to use this variable, then probably the answer would be uh, the operation that we have calculate using the for loops and using the initial value of this variable. So the next task is to assign the same value, example 2012, to all the elements of the array. So we have declared two variables, which is int I and the array numbers 5. So for I is equals to 0 and I is uh, less than 5, is greater than 5, and I increment. And numbers I then equals 2012. It is also in the same, the same process on how we declared or how to use or the syntax in the array using, and don't forget to use for loop. Now let's try to rearrange the elements of the array. Reverse the order of the elements. Let's swap around first and the fifth as well as the second and fourth element. The third one will leave untouched. Great. So the question is, how can we swap the values of two variables? So how to swap those two variables? So let's look in the snippet in the editor. If we do something like this, we would lose the value stored previously in variable 2. And changing the order of the assignments won't help us. So fortunately, we need a third variable that serves as an auxiliary storage, right? So in this case, you cannot get the final answers since we need another variable that serves as an auxiliary storage. So here, as you can see, um, how can we swap the value of variable 1 and variable 2? So in this editor, we have declared three variable, which is variable 1, and it has a value of 1, a variable 2, it has a value of 2, and we have the variable auxiliary. And so how to do this is just like just write the auxiliary, and then it is equal to variable 1. So probably auxiliary have the temporarily have the value of number 1 since variable 1 have the value of 1. And for variable 1 is equals to variable 2, and then variable 2, it has the um, value of auxiliary, which is declared on the first statement. So here we don't know how you feel, but we definitely do not like this. It's acceptable with an array of 5 elements, but with 99 elements, it certainly wouldn't work. So swap the elements 1 and 5. So here, as you can see, auxiliary is equals to numbers, uh, this array, number 0. Then number 0 is equals to number 4. Numbers 4, auxiliary, swap elements number 2 and 4. Auxiliary numbers 1, auxiliary numbers 1, and number 3, and auxiliary. So your question may be, why is it 1? So as you remember that we have the element 1 and its value is uh, number 2, its index. All right, so just like this one, and 1 and 5. So the value of uh value of array numbers 4 is equals to 5. And if we are going to swap the elements with this array, it wouldn't work. It is only in the integers. So let's employ the service of loop. Look carefully at how we manipulate the values of indices. During the first turn of the loop, the I variable will be equal to 0. So the instructions in the body will actually perform the following operations. So auxiliary is equals to number 0 for this array. Number 0 is numbers 4 plus auxiliary. In the second turn, I will be turned to 1, so execute auxiliary numbers 1, and numbers 3, and numbers 3 equals auxiliary. As you can see, the loop does the same job by shortening the code, the source code, and making it more readable. So uh, in this Alright, so as you can see in the editor, we have declared a for loop. So we have I is equals to 1 and then semicolon. I is greater than 2 and I increment and then auxiliary is equals number I and then numbers I is equals to numbers 4 minus I and then numbers 4 minus I equals auxiliary. Alright, so now let's have the next slide. Okay, so sorting an array. So if we can effectively jungle the elements of array, it's time to get on with sorting. This is a serious issue and many sorting algorithms have been invented so far, which differ a lot in terms of in speed as well as in their complexity. But going to show you a very simple algorithm, uh, easy to understand, but unfortunately not too efficient. It is used very rarely and certainly not for large and extensive arrays. So the array can be sorted into two ways. So it is increasing and this and decreasing. So the first one is increasing, or more precisely, non-decreasing. If in every pair of adjacent element, the former element is not greater than the latter. So let's have decreasing, or more precisely non-decreasing, if in every pair of adjacent number the former element is not less than the latter. So in the following sections, we're going to sort the array in the increasing order. So the numbers will be ordered from the smallest to the greatest. Here's our array. So we have 8, 10, 6, and 2 and 4. So we will try to use the following approach. We will take the first and second elements and compare them. If we determine that they are in the wrong order, the first is greater than the second, we will swap them around. And if they're in the right order, we will do nothing. At a glance at a table confirms the second condition, the elements number 1 and number 2 are in the proper order, as 8 is less than 10. Now look at the second and third elements. They are in the wrong positions. We have to swap them around, and let's do it. So we can go further and look at this third and fourth elements. Again, this is not what it is supposed to be like. We have to swap them around. So now here, as you can see in this picture or figure, we are going to switch 6 and 10. And now we check the fourth, fifth element, and well, yes, there are two wrong position. And then we are going to swap 2 and 10. We are going to put 10 in the last, 8 in the second to the last, then 6, and 2, 4 in the first part of the array. So the first pass through the array is complete. We are still far from finishing our job, but something curious has happened in the meantime. The largest element, which is 10, has gone to the end of the array. Note that this is where we want it. All the remaining elements form of the picture's queue mass, but this one is already home. So now we have a moment, for a moment, try to imagine this array is slightly different way. Namely, this is 10, 4, 2, 6, and 8. Look, 10 is at the top. We could say that it's floated up from the bottom to the surface, just like the bubbles in the glass of champagne. The sorting method derives its name from the same observation. It is called bubble sort. We had a quick break with a glass of champagne, but it's time to get back to sorting. We do it with pleasure. Starting with the second pass through the array, we look at the first and second elements. A swap is necessary. Um, and now the second and the third element, yep, it is 8 and is a bubble and goes up to the surface. Time to the third and fourth elements and we will swap them too. So here we are going to swap this, and then the second pass is finished and the 8 is already in place here. So 8 is already in place, and then we start the next pass and immediately watch the first and second elements carefully, and yes, it is time for a swap. So what do you think is the next thing to swap? So let's check the next slide. So here now 6 wants to find its place and we will help it and swap the second and the third elements. Hey, look at the array and it's already sorted. We have nothing to more to do. This is exactly what we wanted. As you can see, this is our algorithm is simple. We compared the adjacent elements and by swapping some of them, we achieve our goals. And in the C language, we try to code all actions performed during the single pass through the array, and then we consider how many passes we actually need to perform. We haven't studied this yet, and we will discuss it more later, right? So next, um, sorting data in real life and computer memory. So how many passes do we need to sort the entire array? So we answer this by doing the following. We introduce another variables. Its task is to observe if any swap was done during the pass or not. And if there was no swap, then the array is already sorted and nothing more has to be done. So we declare the a variable named swaps, and we assign a value of 0 to it to indicate that there were no swaps, otherwise it will be assigned to 1. So here, if you are going to relate this in computer programming using C language, so swapping those arrays into increasing increment of form. So here, as you can see, we have comments in every statement. So arrays to be sorted. So this variable is a variable for the loop, and this one is auxiliary variable for swaps. So now we need the 5 minus 1 comparison. We need 5 and 1 comparisons. Why? So let's check. So the first one is here we have 4 loops. So I is equals to 0 and I is greater than 4, and then I plot increment. So let's compare adjacent elements. So we are going to declare an if else statement. So as you can see here, we have numbers I and uh, is greater than numbers I plus 1. And then if we went here, it means that we have to swap the elements, right? So using the variable ox is equals to numbers I, which is an array, and numbers I and is equals to numbers I plus 1, and numbers I plus 1 is equals to ox. All right, so this would be the code for the swapping the uh, values into increasing order, I mean. So you shouldn't have any problem reading or understanding the program. Int numbers 5, int I, ox, int swapped. Or we can have here, as you can see, we have a do while loop. So, excuse me. So decide if we need to continue this loop. We have swap is equals to 0. No swap occurred yet. So this is only a comment, right? Okay, so remember this is only a comment. So inside the do loop, we have swap is equals to 0, and then we have semicolon, and then probably the closing curly bracket of this is this one, right? So we will have the while a keyword outside the do loop, and then after that we have for loop. I is equals to 0 and I is greater than 4, and then I increment if numbers I is greater than numbers I plus 1, and then swap equals 1. Ox is equals to numbers I is equals to numbers I plus 1, and numbers I plus 1 is ox. While swap. Alright, so look at the editor. You can see the complete program there, enriched by the conversation with the user to enter the print element in the array. So if you already done reviewing this code, let us run this one since it has the header and it's the who body for the function and who the program was written completely. So enter the value 1. Let's have example 1. Enter the value 2. Let's have 2. Oh, another one. Let's have 1. Enter. Let's have 2. Enter. Okay, let's have value 3, which is 3. Uh, so as you can see, I have the value 1, 2, 3, and 4, and 5, and the sorted array would be this one. So it is increasing. So let's try another value for each variable. Let's have 5. So here I try another value for the value of 1 to 5, and I enter different value 5, 4, 6, 9, and 8, and the program sorted it to increment. So why it is increment? As you can see, in the for loop we have increment, right? So that will definitely uh, the answer why it is increment. Right, so now in increment form. So now let's have the next slide. All right, so initiators, a simple way to set an array. Yes, you can initiate arrays. Assign initial values to them at the time of declaration. We do this slightly different than when initiating as scalars. And then because we need to specify more than one value, the syntax of an array, to be precise, a vector initiator is quite simple. Imagine that we want to create an array where the value of any element is equals to its index. A suitable initiator will be as follows. So int vector 5 is equals to curly bracket 0, 1, 2, 3, 4. So as you can see, the vector initiator is simple list of value enclosed inside curly brackets. If you provide fewer values than the size of an array like this, nothing bad will happen. The compiler determines that those elements for which you did not specify any value should be set to 0. So we have int vector 5 equals um, 0, 1, 2. So here as you read this one, the compiler determines that those elements for which you did not specify any value should be set to 0. So we have set only 3 elements here, and the remaining 2 elements is set to 0. So if you provide more elements, then you can be stored in an array like this. Int vector 5 is equals to curly bracket 0, 1, 2, 3, 4, 5, 6. What will happen? You will get an error. Some old compilers can notify you without stopping compilation. This is called compilation warning. It's a good habit to treat warnings with the attention they deserve. So if you have only 5 elements here and you probably give 6 indexes, this is 7 indexes, you will probably get an error. Alright, so be careful on giving the uh, indexes for each element. So one more example, like look at this int vector. So we have no value after in the array. We have 0, 1, 2, 3, 4, 5, 6. We haven't specified the size of the array, but we have provided an initiator. This is legal and will force the compiler to assume that the size of array is the same length of the initiator. So the vector array will be considered declared in the following way. All right. So it is okay to have this one because the compiler will assume that the size of the array will be the same as the length of the initiator. Okay, so now let's have the next slide. Not only ints. So far we have discussed vectors whose elements are of type of int only. Don't be misled. You can use arrays of any other types. For example, this is an array in which you can store 10 floating point values. Float and then float are 10, and you can store 20 characters here. The latter array will, however, be treated a little different by the compiler. Its initiator will be different too. This is why we would prefer to discuss it later when we begin the chapter of strings. Char surname 20. Right. So let's have the next slide. We can only we could also use other types, not data types, not only in ints, but other data types, just like this one, float and character or char. So let's have pointers, the absolute basics. Pointers are also values, but are different from those who've operated with those. So far, the types which we've used are closely linked to computer data processing but have reflected our ideas and our intuition. All of us use integers in everyday life to count all countable things. We use floats when we pay for something and chars when we arrange an alphabetical list of guests at the family celebration. So pointers have no simple analogy to our daily lives, and their values are unreadable to humans and completely useless. Computers, however, can make a great use of pointers, giving developers powerful capabilities when designing algorithms and data structures. We prepare for the fact that not everything will seem obvious at once. This is normal, and it will take some time before you accept the pointers themselves and their specific traits. You may remember that we dealt with pointers some time ago when we used the scanf function. It was a very simple exercise, but now we're going to plunge it into much more complicated issues. Modern computers have large, fast memories. You know that the memory size is expressed in units called bytes. And do you also know that when you declare any variable um, for uh, example, it is an obvious and simple way that the variable occupies a little space of the computer memory. So far, all we've needed to know is what value is stored in the variable. From now on, we are also interested in where this value is stored. Let's trade off the data to say it more formally. The attribute is often called as the address. We all live in certain addresses, just like every variable lives at its addresses too. Try to see the important difference. The value of the variables is what the variable stores, and the address of the variable is the information about where this variable is placed or where it lives. Um, Pointers are used to store information about the location or the address of any other data. We can say that the pointers are like signposts. They does they doesn't have um, anything about the place itself, but they show clearly how to reach it. Right? So we have creating a pointer. Let's start a new adventure with a simple declaration and unequally simple operation. We will encounter a few new operators too. So we have int asterisk p. This declaration sets up the variable number p. It is not an int. The presence of the asterisk means that p is a pointer and will be used to store the information about the location of the data of type int. So pointers are always used to point to specific data referred to in the declaration. The C language can use amorphous pointers too, which can be used to point to any data of any type. But we are going to discuss them at the very end of the story. What is the type? The variable p. There are a few answers identical in meaning, but considerably different. First, we can say that p is a variable of type pointers to int. Secondly, it would be a follow. P is a variable of type int, asterisk where asterisk reads simply as asterisk. Um, Assigning values. How do we assign a value to a pointer variable? Can we assign a value to the pointer? Of course we can. In the same way, you can assign any value to any other variable by using equal operator. More important question is which values are we allowed to assign to the pointers? Using a literal is not an option. The compiler will, of course, allow you to write something like this. But if you think that you know what's stored in the computer's memory at the address 148324, then you are clairvoyant and computer programming is just a waste of your time. So P is equals to 148324. Right? So how about null pointers? So there's one distinctive exemption. You can assign 0 to the pointer variable. Doing this doesn't prompt any questions from the compiler. P is equals to 0. A pointer which is assigned the value of 0 is called a null pointer. As in Latin, nullus means none. It doesn't point to anything. It's like a signpost with all the writing removed. It still exists, but with no purpose to the traveler. Despite appearances, this pointer can be very useful and sometimes even necessary due to the fact that assigning a value of 0 to a pointer variable sometimes causes misunderstandings and mistakes. Some may confuse the pointer for the variable of the type int. There's an unwritten agreement that the developers will avoid assigning null pointers. Instead, they should follow this next convention. So P is equals to capital NULL. The null symbol is actually equal to 0. It looks like a variable, but you cannot modify its value. It's called a macro. We will tell you about it in the module 8 of this course. The same convention also says that the null should be assigned only to pointers. This is the matter of care and elegance with regards to the programming style. We have one caveat. If you want to use the null value symbol, you have to include one of the following headers file. So stdio.h or stddef.h. So the null symbol is defined there. Okay, so remember that if you are using null symbol, you are going to declare the following header files. So whether it is stdio.h or stdef.h. So how do we assign any meaningful value other than null to a pointer? We may assign to the the pointer a value which points to any already existing variable. To do that, we need an AND operator called the reference operator. This is a unary prefix operator. The operator simply finds the address of its argument. See that statement. Here, as you can see the statement in the snippet, p is equals and I, and after completing the assignment, the p variable will point a place where the I variable is stored in the memory. This can be shown in the following way. So here, this is how it was stored in the memory. So p is equals and I. All right, so how about if you assign a null to the pointer? So it will look like this. So if p, this is a variable, if the pointer is equals to null, then from now on, the p pointer points to neither the I variable nor to any other variable. We can use the following symbols to express this. As you can see, p pointer is grounded. And what can we do if the pointer is not null and points to a value? We can dereference it. So dereferencing is an operation by which the pointer variable, as we will see later, it is not only a variable but also an expression that yields a pointer becomes synonymous with the value it points to. Look at how we declare variable of types. So int ivar and a variable of type int, and here asterisk ptr, we can do it within a single statement as shown below. So here int ivar and then it is a pointer, asterisk ptr and then semicolon. So now let's assign a value of 2 to the ivar variable and everything's clear so far, right? So how to assign this? Ivar is equals to 2, and now we will make the pointer or ptr point to the ivar variable. So how to do that is ptr and then equals and then ampersand ivar. So that is how to make the pointer, how to make the ptr pointer point to the ivar variable. So how do we get a value pointed to by the pointer? We have to use well-known operator, the asterisk, but it is a completely new way as a dereferencer. If you place an asterisk in the front of a pointer, you can get a value which is stored at a location pointed to by the pointer. So here, just like this one, asterisk and then PDR. So that is a dereferencer. So the following invocation will display 2 on the string, and the printf second argument is the referenced ptr value. Note that the ptr points to ivar and the ivar is equals to printf and then %d, and then we have the pointer asterisk ptr. If you write a statement like this, like one here, asterisk ptr is equals to 4, you won't change the value pointer value. You will instead change the value pointed to by the pointer. This is very important difference. Don't forget that if you declare a pointer in the following way, any, then underscore type, and then asterisk pointer, it means that the pointer variable is one of the type any underscore type asterisk. The asterisk pointer expression is a type of any type. Notice that the place of asterisk occupies in both cases. If you use avoid as any type, then you create a valid pointer to some memory but interpretation of pointed value belongs to you. We have to mention that you can typecast pointers, but it is in many cases but bad practice. Think twice before you do this. Also, don't forget that the referencing null pointers is strictly forbidden and leads to a runtime error, which stops the program execution at once. So let's have this slide. So all right, guys, this will end our session, our third session, and we will continue in this on the fourth session for the 25 more slides for module 4. So remember that we have ended on the slide another new operator, and after the 25 slides in the next session, we will have the module 4 quiz and module 4 test. So this concludes the third session of the Diverse Node Mobility Front-End Development Program. Have a good day and God bless.